Hello everyone, welcome back. So today we will discuss how the transformations related to the angular velocities are computed from one reference frame to other reference frame. So earlier we had discussed that how we use the aerospace convention or the sequence, that is psi theta phi, to obtain the vector which is in the inertial reference frame from the body reference frame. So we had seen how we need to perform this psi rotation, then this theta rotation, and at the end we need to perform the phi rotation, and we had obtained the transformation matrix that is in this form, right? So let us proceed further. So today's topic is Euler angle rates. Okay, so this is a part of the axis transformations. Okay, so as an engineer, you'd need you'd often need the time response of the Euler angles. For example, I mean, how does the plots of the Euler angles look like? So I'll draw it here. So if this is your timeline, so this is t axis and this is any value, this is the magnitude, so this is magnitude. Okay, so this is any parameter or any signal you are interested in. So if initially your parameter was something and your desired is something, so the time response looks something like this. Okay, so suppose your your body was initially at some angle, then after some time it underwent some transient behaviors and then to steady state. So this is one example of the time response of the Euler angles. So this might be a psi or theta or phi, any angle which we are interested in. So if we are interested in 3 parameters simultaneously, then we will get 3 such curves simultaneously, right? Or if the aircraft is undergoing various maneuvers, then these plots would be these time responses would be different according to the maneuver that vehicle is undergoing. Okay, so to obtain these parameters and the related time responses, we need to compute these parameters at each time instance, and to do so we need to have the knowledge of the time derivatives of these parameters. Okay, So if we know these parameters, then we can integrate to get these plots. Okay, but usually these are not directly measurable in an aircraft, or these are not available from the instruments directly. So in order to compute this, we need to rely on the measurement units or the data available from the aircraft instruments. So in the aircraft, we usually use the rate gyros. Okay. So these rate gyros give us the angular velocities of the vehicle in its body coordinate system. So those angular velocities in its body coordinate system, suppose we will write it is omega b, then it is like p, q and r. So this is the x component, this is the y component, and this is a z component. Okay, so this defines the angular velocity in its body coordinate system. Usually the aircraft's instruments or the rate gyros give you these information directly. So these are measurable directly in its output. However, we need these values in its inertial frame of reference. So what we need to do is that we need to transform from its body frame to its inertial frame. So how do we do so? So let me draw the body reference frame again. So it is xb, and this is zb, and this is yb. Okay, this is origin. And similarly, the inertial reference frame can be drawn in this fashion. Okay, xi, yi and zi. Okay, so now we want to compute what would be its Euler rate in the body reference frame from the knowledge of the Euler rates in its inertial reference frame. So that can be done using, let me do it for psi, because we are following the 3-to-1 convention or psi theta phi convention. We will proceed with psi first. So psi dot b will be equal to a b and then the inertial frame vector. So 0 0 psi dot I, right? So this is psi dot I and this is psi dot b, and these are AB. AB matrices we had already discussed earlier, right? So A is the transformation matrix. A is the transformation matrix when we do the rotation phi. Okay, and B is the transformation matrix when we do the rotation theta. Okay, so as we are dealing with psi dot or the rotation around about its z axis, so psi dot is moving, right? It is rotating. So once it is rotating, that vector which is the angular velocity vector, that needs to be further transformed twice. Once about its theta motion, and once about its once for its phi motion. Okay, that's why we are doing it for B and A. Similarly, okay, next we will do for theta dot, right? So theta dot B will be what? So this is in sequence manner. So we have already done A, B for psi dot. Now theta dot is there. So theta dot has to be done. I mean, how many times it has to be transformed? So these two has already been done. So we are left with, I mean, we need not to do anything with psi anymore. I mean, it has been transformed. So from theta, next we have to do phi. So we need to do it once from here. So that is about phi only. So that will give us 0 theta dot I, and this would be 0, right? And lastly, it is phi dot B equal to phi dot I 0, 0. So here there is no transformation matrix involved, because after this there are no rotations left. Okay. So now we can write this angular velocity vector in terms of these body reference frame Euler angle rates. So that can be written in this fashion: omega B equal to, which is PQR, that is equal to psi dot B plus theta dot B plus phi dot B. Okay, so these three vectors need to be added. Okay. So now after this, so P, Q, R, this can be boiled down to 1, 0 minus S theta means sin theta, this is 0, then C phi cos phi, then sin phi cos theta 0 minus sin phi cos phi cos theta. Fine. So this side, this is phi dot theta dot and psi dot, right? So these are in their inner cell frame. So these are inner cell frame. Okay, these are inner cell frame. Okay, so now, but our goal is to obtain the angular velocities, or more accurately speaking, the Euler angle rates. Okay, so our goal is to find these Euler angle rates in the inner cell frame of reference in terms of the body rates, not the other way around. This equation shows the other way around. So we need to take this matrix inverse and multiply here both sides. Okay, so that can be done in this equation, that is phi dot, theta dot and psi dot in the inertial frame will give us 1, then this is tan theta, then sin phi, then cos phi, tan theta, then 0 cos phi, then minus sin phi, then 0, then sec theta, then sin phi, then sec theta, then cos phi. Okay, P Q R. See, as earlier we were seeing those transformation matrices were orthogonal, this particular transformation matrix is not orthogonal. So to find this, the inverse of this, which is this matrix, we need to perform any usual method of we need to follow any usual method of inverse of a 3 cross 3 matrix. Okay, so this is a very important set of equations. So this equation shows the relationship between the Euler angle rates in its inertial frame with the body fixed angular velocities. Okay, so why this is not orthogonal? Because phi dot, theta dot and psi dot, so these are not orthogonal. Okay, so these are not orthogonal, and because of that it is not orthogonal. Okay, so we'll see now. See, this equation is very important. Wherever you see any aircraft flying, moving in air, it is definitely using this kind of I mean, it has to compute these equations. Otherwise, there is no question of the vehicle can take off and do any kind of flying maneuver. So either it has to do this equation or some similar equations, but this kind of relationship, I mean, this may change, but these two remain the same. Okay, so inertial frame Euler rates and the body fixed angular velocities have been transformed in this manner. Now, as we had already discussed, that each of these transformation methods have their own limitations, right? So one such limitation associated with Euler angles, Euler angle rates, is the issue of singularity. Okay, so that's why we say that there are different options. So there are different methods of transformation. So each method has its limitations, each method has their advantages. So one of the limitations is this. So Euler angle rates suffer this issue of singularity. So how does it happen? Let us see. So we can write these equations in a more elaborate manner. So that is phi dot equal to, I am not using I, you please understand. So phi dot equal to, I am just writing these equations, okay, the same equation, I am just expanding it. So phi dot equal to P plus Q sin theta sin phi plus R sin theta cos phi divided by cos theta. Okay. Similarly, theta dot equal to Q cos phi minus R sin phi. Okay. Next, psi dot equal to Q sin phi plus R cos phi. Okay, divided by cos theta. So the limitation arises when theta becomes, theta means the pitch angle, okay, or the inclination, okay. So theta becomes pi by 2. So once theta becomes pi by 2, just put it here, the value of theta, wherever you see theta, you just put pi by 2. So these equations boil down to P equal to phi dot minus psi dot. Similarly, Q equal to theta dot cos phi, and R equal to minus theta dot sin phi, right? So these three equations we obtain when theta equal to pi by 2. So let us put these three equations here and let us write it down again. So what does we get? So see, now we'll write this psi dot equation. So psi dot at theta equal to pi by 2 becomes what? Theta dot sin phi cos phi minus theta dot sin phi cos phi divided by cos theta. Okay, which is 0 by 0 form, or it is called indeterminate form. So we cannot compute it, right? So this is the singularity issue we were talking about. So at theta equal to pi by 2, these equations, while you will be intending to find the values and to integrate these equations, you see these values itself are giving indeterminate form. Okay, so and if you are practically you are implementing it somewhere in some computer or microcontroller or somewhere, these kind of values will give you, it on the screen it will show only nan, not a number, right? So it will just explode. I mean the curves, I mean the estimations or the computations will simply explode. Okay, so okay, we saw it for psi dot. Let us evaluate it for phi dot also. So phi dot theta equal to pi by 2. So P plus theta dot sin theta cos phi sin phi minus theta dot sin theta sin phi cos phi divided by cos theta, which is equal to p plus theta by theta, which is again indeterminate form. So in practical situation, to get around this difficulty, we can use L'Hospital rule. So let us proceed with the L'Hospital rule and see how we can get around this issue. So okay, so these equations are there, right? So let us write it down for L'Hospital rule. So psi dot at theta equal to pi by 2 equal to limit theta tends to pi by 2. Okay, so now I need to take the derivative of the upper term. So q sin phi plus r cos phi. Okay, now I need to take the derivative of the denominator term d theta of c or cos theta, right? So after computing this, what we should get is this. At theta pi by 2, what is it? 1 by theta dot q dot sin phi plus theta dot phi dot plus r dot c cos phi. Okay, similarly we can also compute for these two, I mean phi dot and theta dot. So what we get, phi dot at theta equal to pi by 2 equal to p by 2 minus 1 by 2 theta dot q dot sin phi plus r dot cos phi, right? Next, theta dot at theta equal to pi by 2 equal to q cos phi minus r sin phi, right? So these three equations we got when theta equal to pi by 2. So if we implement this when theta tends to this, then we can get around the singularity issue. So we need to remember this, okay? And I mean we need to switch when it is required. For example, when theta is not in the neighborhood of pi by 2, we can use these equations, okay? These equations or these equations, this one. So when theta is in the neighborhood of theta equal to pi by 2, then we need to switch our computation from here to here. Okay, so for today we'll wrap it up. In the next lecture we'll see how the quaternions or Euler parameters help us in transforming these axis vectors from one coordinate system to another coordinate system, and how we avoid these kind of singularity issues in the quaternion transformation methods. So yes, if you want to know anything more, then please inform me by writing the comments in the comment section. I'll try my best to come with some more material to offer you guys. So thank you and see you